So this is about a set of research tools that are part of PAID. And I want to tell you that I had plans for live demos and then discovered I couldn't project off my laptop, and then we recovered enough to have some live demos, but I just, my disclaimer is this is not my computer. So CHiLL is something we've been developing for a long time, and we've rewritten it a couple of times. So there's a long list of collaborators. It was the original idea and passion of the late Chen, who worked for me for many years. And I currently have 4 students who are working on it, and a bunch of collaborators who are actively working with me, and people who worked with me in the past. So I want to give credit to all those people. Okay, so here's some code that you're going to see potentially in our live demo. Here on the left is the smooth operator from the mini-GMG benchmark. So it's a geometric multi-grid benchmark. And the code on the left is pretty short. It's 13 lines of code. It's 3 operators that are composed together to be the smooth operator for the baseline mini-GMG. And on the right is the hand-optimized mini-GMG that performs the same computation, and now is 170 lines of code. And this is actually just the sequential code so that I could do a side-by-side comparison. The parallel code is even bigger, okay? And so why is the code on the right so big? And this is, by the way, the target architecture for this work was the Edison that you heard about yesterday from Rich Gerber at NERSC. So there's a bunch of memory hierarchy management in this code. There's prefetch, the data is being staged in registers. There's a lot of explicit AVX SIMD instructions. And when you look at the parallel code, there's a bunch of additional work. There's ghost zones between nodes so that you can share data in the stencil across nodes. There's a trade-off between computation and communication. So there are parallel wavefronts. There's nested OpenMP code, there's MPI code, and then sort of standard OpenMP was not efficient enough on Edison, so it's extremely low-level OpenMP code with spin locks, okay? So this is, and suppose you want to run this code on the GPU, well, you have to start over and write it again, okay? So this is just the kernel code, and it's 308 lines of code, okay? So this is sort of typical if you really want to get high performance on modern architectures. You have to write fairly low level and fairly architecture specific code to get high performance. And so this is probably going to get worse as the architectures that we see are going to be increasingly diverse, and they're going to come on the scenes, and you're going to have to rewrite your code. And that was kind of part of Rich Gerber's message yesterday about KNL requiring a significant rewrite to just get back to the Haswell performance. And it's also the message of the talks in the previous, just before this one. So that means that your code, even if it's portable from one architecture to another, is not performance portable. You're not going to get good performance with the same piece of code. And then there's a productivity question, because if you want to get high performance, you have to write low-level code, and that low-level code takes a long time to get right, and it's big. And then as you move that code from one architecture to another, it's not very portable, and it's hard to maintain because it looks really low-level. So the current solutions that to how people are dealing with the architectural diversity that we're seeing, that people have been talking about here, that you even see on Blue Waters, is to follow the standards. One of the things that's been happening recently is that OpenMP is broadening. OpenMP4 is broadened in a bunch of ways to be able to, for example, talk about accelerators. And so you can follow these standards, and some people believe that, oh, the code will work on either architecture. Well, it may work, but it's not going to be, it's unlikely to be high performance on multiple very different architectures. And then The other strategy that's common is you use a library that encapsulates all of this, that a couple of library experts have developed, or a domain-specific language. But one of the challenges with this is that with any of these kinds of approaches is the lack of composability, that you don't have the context in which these things are being executed under, and you can't compose multiple computations together to get an efficient whole. So that's why we developed CHiLL. It's a compiler optimization framework, and we build domain-specific optimizations in CHiLL in addition to standard optimizations. You'll mostly see standard optimizations today with one example of a domain-specific optimization. And those transformations, because of the kind of compiler framework in which CHiLL is built, are composable, and that means that you can apply a very complex sequence of transformations and get parallel code. Okay, and so the optimization strategy can be specified with transformation recipes. These could be derived automatically. In some of our work, they're derived automatically, but otherwise you have a way of explicitly describing how you want to optimize the code. And then the key idea, and the one that kind of holds it all together, is that CHiLL is designed around this concept of auto-tuning. So you're systematically deriving a search space of possible implementations of the computation, and you're searching those different implementations empirically by measuring on the real hardware to try to find the best solution. And this can be mixed with models and all sorts of strategies to be able to explore this space in an efficient manner. That's not really the focus of our work. We have a lot of partners that we work with to address that problem. I'll give you a little bit of a hint of that in the tutorial, but I'm not going to go into that very deeply. So there's a way of pruning this search space and doing these experiments efficiently. Okay, so the idea is for us to be able to automate the process of generating that code B from code A. And without telling you a whole lot of details in between and a grad student's PhD thesis worth of work, we did, in that mini GMG example, we've published a series of papers where we show that, in fact, we can actually beat that manually tuned code with the compiler-generated code. So this is just one of the graphs. This is the easiest one to read that shows that anytime you have a little green bar above, these are speed-ups over the baseline. Anytime there's a little green sliver, which is most of them, that's when our compiler-generated code beat the manually tuned code. And our compiler-generated code is actually simpler than the manually tuned code, but we're able to optimize some things that we're able to explore a richer search space, and so we can find things that that maybe in manual tuning were too much work to explore. Okay, and it's doing a whole bunch of things. I'll actually show you this example towards the end of my presentation. Okay, so this sort of describes the kind of research we do with CHiLL. So one is we do a bunch of compiler and code generation research and auto-tuning research. And we look at particular application domains with application partners. So I talked about the stencils and multi-grid, done some work on tensor contraction, and then a big chunk of our current research is on sparse matrix codes and being able to expand the compiler support for these. We have DOE partnerships that are similar to the paid projects to speed up HPC application, and then we have the paid projects that are doing that for Blue Waters. And I think that to distinguish paid from SciDAC, for example, the partnership with NCSA means that we're much more integrated into the platform itself. We're also just starting an exascale computing project to look at auto-tuning in the context of some of these application domains. Okay, so, here's the three applications we've looked at. The CPP-Traj, which is the analysis code from Amber, and we showed a 29x speed up doing CUDA code generation. The Milk QCD that Steve Gottlieb, who's in the room, talked about, We improved an OpenMP reduction and showed a 2.4x speed up on that, but we also, I'm going to talk a little bit about milk, and I had a live demo of milk, but that's too much trouble, so I'll have to show it to Steve in private. And then we're working right now, we're kind of at the end of paid, we're working right now with Jamesina Simpson on a FTDT application, and we're not done yet. We've seen a 6.5x speed up compared to sequential. We're trying to integrate that back into her MPI application, and also we think we can get a good GPU speed up with some specialization. We're working on that. Okay, so let me try to explain CHiLL a little bit, and then we'll go to live demo time. So this is a very compiler-light slide to try to explain the underlying implementation and what kinds of transformations CHiLL is able to perform, okay? So it's a polyhedral framework, which means that it represents loop iteration spaces as polyhedra and is then transforms them in that abstraction and does scanning to generate the final code. Okay, so here's an example where we're gonna start with this very simple code. I'm gonna show you something a little more complicated in the example when I do the demo. It's gonna extract an iteration space from that computation, and so that iteration space is that I is from 0 to n, and that's for a particular statement which we're gonna number in the code, and then we actually don't care anymore about what's going on in that statement. We're going to apply the transformations to the iteration space. We care enough to make sure that there are no dependencies, or to build a dependence graph, but we're not going to look at the actual code. So now we're going to apply transformations. So I'm going to do a simple transformation where I'm shifting by 4. I'm shifting the iteration space by 4. And so that's going to give us this, this output iteration space that I is from 4 to n plus 4. And then we're going to generate the code. We now need an inverse of the transformation to figure out what to do to statement S0. And so that inverse is that I goes, it's a relation that I is mapped to I minus 4. And then we're going to generate the code, okay? So that's an example. So any transformation that you can describe as a relation that maps from the original iteration space to the transformed iteration space, you can compose with other transformation, and after you've composed all the transformations together, then you can go ahead and generate the code. Okay, and so how do you use CHiLL? So you provide both the source code and a transformation recipe, which is just a Python script. And where the auto-tuning comes in is you can have a bunch of different parameter values for the transformations, and you can have different scripts that describe completely different transformation strategies, that describe GPU code generation or OpenMP code generation. And then that describes a search space, and then that's provided to some framework that performs the auto-tuning search. And we work with external groups, Active Harmony from Maryland, Oreo from University of Oregon, and OpenTuner, which comes out of MIT. So we're happy to use anybody's search framework. And these search frameworks are doing a bunch of machine learning, heuristic search. They encapsulate a bunch of different kinds of algorithms. Okay, so, and then this is the concept, of a superscript, which is how we describe the search space. So for example, on Edison, there are 12 cores on a node, and I want to try nested OMP parallelization, then I can enumerate all the different kinds of combinations I want for the multi-dimension of the thread counts, and then try them all by just running a search. Okay? All right, so, okay, so now we're ready for an adventure. I had 4 examples I was going to show you, and I'm not using my own computer, so I'm going to show you 2 or 3. We're going to see how this goes. And let's see. So it's Alt. It's Alt Tab. Okay. I have to hold it and then do that. Okay. Yeah.
So I need to just.
I think I was about to get it, but. Okay, so I have to give a shout out to my student, Tuowen Zhao, who built an interface to CHiLL, which he calls CHiLL Online. And so this is perfect for a setting like this because I can actually run CHiLL. So here's that shift example. And on the left is matrix multiply. And on the right is a script to describe that shift at loop level 1, which is the I loop, okay? So I'm going to push this little green button. And at the bottom is the shifted code. So you can see that it's done exactly what I said it was going to do. It's starting the outer loop at 4, and then it had to change all the things that were indexed by I. It had to change to I minus 4. Okay? So the next thing I want to show you is that Jacobi, that example from the beginning of my talk. Okay, this is where and the interface, you actually have to put all the include files to there, but that's not true of actual CHiLL. But in the CHiLL interface, you have to explicitly have all the include files. So this is that code with all the include files, and it's a Jacobi, so it's doing an in-place update. And so, well, let's get past that. So it's a little bit longer than the 16 lines, but it's not very much longer. So here's the code. It's doing the stencil, and then has to do it for the even case and the odd case. Okay, and here's the transformations that I want to do on that code. So I'm going to do this skew and permute. That will give me a parallel wavefront, and then the stencil temp is a transformation. Is a domain-specific transformation for higher order stencils. It allows us to buffer the data. Stencils are really bad with SIMD extensions like AVX because you're shifting the window of the data that you're looking at as you do each iteration of the inner loop. And so stencils have this really bad memory behavior, and this partial sum transformation is designed to buffer that data in an aligned way and also get rid of redundant computation so that you can take a higher order stencil and make it less compute bound. So that's what's going on here. And so I'm going to transform the code. Yeah, there. And it's going to produce some optimized code. And for example, you need to look for the buffers. The buffers, for example, are this domain-specific partial sum transformation. So it's producing architecture-specific code, but you didn't have to write it. So that's the basic idea. Okay, so now I'm going to have a real adventure, and I'm going to try to bring up the CUDA code generation. Okay, so this is CUDA code generation, and so this we have a thin layer called CUDA-CHiLL that allows us to generate CUDA code. And on the left here is the MRIQ. I thought it would be cute since I'm at a UI/UC meeting to have one of the parboil benchmarks. So this, in fact, this is in Wenmei's book. So a couple of things I was going to show you, I can't show you, but here we are. We're going to generate CUDA code. And on the right, we have a couple of things going on. We have all the tile sizes are being set, and so that allows us to adjust the thread and block decomposition for the GPU. And that actually turns out to be a huge payoff in terms of an auto-tuning optimization, just trying different thread and block decompositions, because every time you move from one GPU to another, that trade-off changes radically just because the number of cores changes. And so that's what those TITJ are. The N and M are the problem sizes for the computation, and a bunch of stuff is commented out here. But this tiling is allowing us to set up, if you read Wenmei's book, this computation on the right, the loop you want to parallelize is that inner J loop, because the I loop is sequential, it has a dependence, you'd have to do something really expensive in order to parallelize it. So you want to parallelize the J loop. And so we're going to make our thread and blocks from the J loop. We're actually going to tile the J loop so that we have thread and blocks, and then we're going to generate the code, okay? And this is, for some reason, generating, showing the code before it's completely generated. So what happens, but it's kind of interesting from a talk perspective, what happens here is you see that it says CUDA preferred index BX, so that's the block X, and so that loop is actually going to go away when the final code is generated. And then the preferred index II, that's actually going to be inside the thread code. The preferred index TX, that's thread X, et cetera, okay? And so that stuff is still in there for some reason. And then it's also generating the code, the mallocs and the copies and all those low-level things that you have to do to get the data to the GPU, okay? So let me get back to my talk. Okay, that was easier than I thought it was going to be. Okay, and I was going to do a milk example, so I'll just kind of talk about it. So, this is in honor of Steve being in the audience. So there's an operator in milk from QCD that is called Dflash, and this particular piece of code, every time they target a new architecture, they rewrite it, okay? And the data layout that you need for different architectures is completely different as you move from one to another, as you look at different SIMD kind of support and the granularity of parallelism that you're trying to reach. And so this is actually something we did before paid with this code. There's a complex matrix vector multiply that's the core part of Dflash, and it's complex numbers. And so you can see that this is sort of separating the real and the imaginary parts and doing that 3x3 matrix vector multiply. And so on the right is some actual Dflash code that was targeting SIMD with regular ABX and a kind of conventional multi-core. And so what they did, what the code developers did was actually unroll the thing completely and then did a whole bunch of hand replacement of the scalar variables. And so you take a piece of code that starts out 7 lines of code, and it's 72 lines of code in the software that is run for that kind of target architecture. And so this was so the example was just going to show that you could very simply generate the code on the right or something comparable to the code on the right from the code on the left. Okay, and yeah, so I was going to show you the optimized output for MIRIQ, but let's just move to the end. Okay, so the idea of our project and our research is to develop auto-tuning compiler technology to give you performance portability on modern architectures for the kinds of application domains that arise in HPC. And one thing that we've proven with our research is we really can achieve the level of performance that people get from manual tuning, but the input code is something much more compact. And you do have to do it in conjunction with expressing how you're going to transform that code, and so that can be very complicated, but some of our research revolves around developing those recipes in an automated fashion, and we're doing a bunch of work with machine learning to derive those recipes or to prune the search space of possible recipes. I just had a couple of things to say about my experience in paid. This was first time working with the facilities team at this level of closeness, and I think it was really interesting to understand how to support users in a more in a more professional way, shall we say. And we've done a lot of software improvements. We were inspired to do a lot of software improvements to be able to release and have users and things like that. And did a fairly significant rewrite during our time on this project. And then here's the important thing and why this kind of program is interesting to me. As we look at these application codes, we always learn new things. We learn what are the challenges, particularly if we look at new architectures too. So if you look at applications you've never seen before and you look at new architectures, then you can't just do what somebody did before manually. You have to come up with new ideas, okay? And so I was talking to Steve yesterday about data layout optimization in the context of Milk so that you could generate these different versions that they need in a more automated fashion. There were, when we worked with CPP Traj, we were working with C++ code, and so we found some barriers to using C++ in the context of our tool. One of them is not really a barrier. They use C++ iterators, but if you want to transform to thread and block indices, you really need stride 1, something that looks like a C for loop. So that one actually was more like you need to do that to be able to generate the CUDA code, but for example, it uses a vector library, and we're not doing much to the vector library. As long as we know it doesn't have any side effects, we should be able to support it. And then finally, there's some interesting research on FTDT and how to specialize depending on the coefficient matrix, because sometimes it's either constant or it has a pattern, and you don't actually need to do all the computation. There was actually a talk on Wednesday that used a similar idea where you recognize that you've got a pattern. Instead of doing every single multiply, you can you don't have to represent all that data. You can have a subset, and that will help speed that code up as well. So this is the fun part, is finding these new ideas in the applications that we look at. So with that, I'll take questions.
Thank you very much.
Thanks for your patience.
Questions? Any? Well, audience, wait. Thinks about it. Oh,
There's a question.
I was first, but okay.
So the examples that you showed always had the transformation script on the right-hand side. So right now, I guess you're working on generating these automatically through some type of learning algorithm. But how much hand-tuning does go into these things in the end? So.
Oh, we don't touch the code after we...
No, the transformation scripts that were shown in your example on the right-hand side. Sorry, the right-hand side.
You're saying that transformation script is like hand tuning. Is that what you're saying?
Probably not completely, but there's certainly some expertise that goes into it, I guess.
That's right. So the answer to that is either you automate generation of that, and the places where we've done that and it's been successful is if you're focused on a particular domain, or you have a particular tool that's generated the, some tool where you've been able to express what computation you want to do, or something where it doesn't have to be the general purpose solves all problems kind of thing, because that's where compilers start to have trouble when they're trying to be everything for everyone, right? You can do a whole lot better if you're specialized. So we have automated it, and I have a student who's really excited about machine learning algorithms to try to come up with the search space in a very general way, and then also in a domain-specific way. So one answer to your question is automate it, and then everybody's happy. The second answer to your question is have an expert come up with the possible set of scripts in a particular domain, or a set of examples, or something like that, and then teach other people. That's sort of the intermediate solution for this. I mean, one of the things that we tend to do is work in a particular domain, and then you end up with some patterns in those scripts, if that makes sense.
Any other questions? I'll ask a question. So do you think you'll be working on Xeon Phi optimizations in the future? Like some specific?
What kind of optimization?
For Xeon Phi?
Oh, absolutely, like right now. But we haven't done very much yet, but we're actively working on it right now.
Okay, and the next question is how do you verify that,
That's a very good question. In general, what we do is we have like ground truth. Just like what you do often in GPU code, you have like some sequential version and you run it, and then you have the parallel version, and you verify that their results match within some delta, right? The question is, what is that delta, right? That delta can be very application specific. If you're doing integer work, then it should be the same answer. But if you're doing floating point, it's probably going to be different anyway, just going from CPU to a GPU. So it's very similar kind of validation, but that's a question that people doing research in this area have, because imagine that instead of swapping out the code for the optimized code at compile time or tuning time or whatever, suppose I start swapping it while the program's running. Okay, at that point, the validation better be really good. Or the programmer may be a little bit surprised at what happens. And so that's actually a topic of active research. But we do something basic. We just do a side-by-side comparison of the output.
Thank you. All right,
Great.
let's thank our speaker again.